Morning, my dear students. Myself, Dr.D.Raguraman, Assistant Professor, Department of Automobile Engineering at the School of Mechanical Engineering, Bharat Institute of Higher Education and Research, Chennai. This video lecture, we will see the topic Design of Cylinder. It's coming under the course code U18Pcau403 under the course name Design of Engine Components. So before heading into the actual design of cylinder, we will see about the IC engine concept. So if you're seeing about the internal combustion engine, this is a marine diesel engine. If you're seeing this marine diesel engine, this is the concept of IC engine. So what we are going to see is, you are going to see about the design of the cylinder. So in case of a combustion engine, if you are seeing combustion is taking place inside the cylinder. So whatever the fuel intake, that fuel intake is what, either it's a petrol or a diesel fuel, that fuel is going to be get intake here and it is going to get a combustion. During the combustion, you are going to get a power. That power is what it is going to be used for the remaining stroke. That is what in a fundamental level you had already learned. That only it is required to revisit again. So here you can able to see it clearly. See, there is an induction stroke, then a compression stroke, then a third stroke is being power stroke, then exhaust stroke. So now you can see induction stroke is going to come. So just see, if induction stroke is coming, inlet valve is opening. Okay, so when inlet valve is opening, it is going towards top dead center to bottom dead center. Then at the compression stroke, it is coming from bottom dead center to top dead center. So it is compressing the fuel already circulated. So that's what in the compression stroke happening. So that because of the high compression ratio, it is going to get ignited in case of a power stroke. That is what it will be said as a compression ignition engine. Diesel engine will be said as a compression ignition engine. But in case of a petrol engine, you will be having a spark plug. But in case of a diesel engine, you will be having a fuel injector alone, and you are not having air fuel mixture. Instead of that, you, because of the high compression ratio, it is going to get a combustion. That's what. In case of a power stroke, you can able to see the third stroke, it is coming from the top dead center to bottom dead center. Due to the combustion power, the piston is going to make a movement inside the cylinder. So what we are going to design is, we are going to design the cylinder. That is what we are going to see on this topic, how to make a design of a cylinder. So the cylinder is what? It is outer coverage for the piston. Piston is going to reciprocate inside the cylinder. So cylinder is what? It is a hollow section. So inside the hollow section, you are having a solid shaft. So solid shaft is what? It is a piston. So you can able to see piston rings also here. So this is valves. You can able to see A is valve, this is valves, and you will be having rockers, and you have a camshaft. The camshaft is what actually it is making operating upon a valves. Inlet valve and the exhaust valve, it is getting opening at an exact timing. So that the timing is what it is designed by means of an timing gears, so that you are going to have an injection of a fuel at the exhaust stroke. That is the power stroke. You are going to get a exact combustion. So that is what you have. Every component it is available on this GAF. You can able to see. So the valve mechanism, everything, and you will be having a injector, fuel pump, lift pump. Everything is mentioned on this PPT. Okay. But our aim on this video lecture is what we have to concentrate about design of a cylinder. So we will in depth you are going to see about how to design the cylinder. So we will head into cylinder introduction and the design procedure of a cylinder. So now about a cylinder, the function of a cylinder is what it is to retain the working fluid and to guide the pistons. As you had already seen in the working function of an IC engine, cylinder is what it is going to retain the working fluid as well as it is going to guide the piston. So the cylinders are what? It is usually made up of cast iron as well as cast steel. And since the cylinder has to withstand the high temperature, because as the fuel is going to get a combustion, it is going to have a high temperature. So the cylinder should be designed in such a way that it has to be kept in mind it is going to have a high temperature due to the combustion of fuel. Therefore, some arrangement must be needed to cool the cylinder. That is what you have to make a cooling system in the cylinder liner also. Okay. So that is what you had a single cylinder engines. In case of a scooter and motorcycle, if you are seeing, that will be a single cylinder engine that are generally air cooled. That's what you will be seeing fins. So you had a fin system for engine cooling. and others you will be having a radiator system. So they are what provided with fins around the cylinder. In case of a two-wheelers, it is provided with fins. And in case of a multi-cylinder engine, such as cars as well as heavy vehicles like lorries, buses, all this thing, it is provided with water jackets around the cylinders to cool it. So now about the cylinder liner. So in the cylinder liner, in case of a smaller engine, the cylinder, the water jacket and the frame are made as a one piece. But for all the larger engines, these parts are manufactured separately. So the cylinders are provided with cylinder liners so that in case of a wear, they can be easily replaced. So the types of cylinder if you are seeing, you will be having a dry liner and another one is being a wet liner. So the dry liner, if you are seeing, this is the schematic representation of a dry liner. The dry liner, you can able to see the water jacket. It is not close to the liner, so water jacket is kept apart from this liner. And in case wet liner, if you are seeing, that is kept just touching this cylinder liner. Okay, so that is what a wet liner. Now, if you see what is the classification further, okay, so you are seeing the details. What is the dry liner as well as wet liner? If you see the dry liner, a cylinder liner which does not have any direct contact. The cylinder liner which does not have any direct contact with the engine cooling water. The cooling water is going on here, and the cylinder liner it is not having any direct contact. That is what you will be seeing as a dry liner. But the case wet liner, you can able to see here you are having a direct contact. So a cylinder liner which have its outer surface in direct contact with the engine cooling water is what it is known to be as a wet liner. So the cylinder liners, it is what it is made from good quality close grained cast iron. That is what usually pearlite cast iron, and also it is made with nickel cast iron, nickel chromium cast iron. Because as already mentioned, it has to withstand the high temperature. Because of that, the cast iron can withstand a high temperature. So we are going with pearlite cast iron as well as nickel cast iron and nickel chromium cast iron. And in some cases, nickel chromium cast steel with molybdenum also can be used. So the inner surface of the liner should be properly heat treated in order to obtain a hard surface to reduce wear. So whenever we are going to design the cylinder, then we have to consider these four main things: the specification, that is thickness of cylinder wall, and the second one is being bore and the length of the cylinder, and the third one is cylinder flange and studs, and then cylinder head. Fourth one is cylinder head. Now we are going to see the design procedure one by one. First thing is being a thickness of cylinder wall. So the thickness of cylinder wall, if you are seeing, that will be subjected to a gas pressure and the piston side thrust. So the gas pressure, that will be what it will be producing the two types of stresses. The type of stresses by the gas pressure is longitudinal stress and circumferential stress. So since these two stresses act at right angles to each other, therefore the net stress in each direction is reduced. And the piston side thrust, if you are seeing, it tends to bend the cylinder wall, but the stress in the wall due to the side thrust is very small and hence it may be neglected. So while seeing how to make calculation of a thickness of cylinder wall, we have to consider few notations. So DO as well as a capital D. DO is being what? Outside diameter of the cylinder, and capital D is inside diameter of the cylinder. Because if you see the cylinder, that is being a hollow shaft. A cylinder is being considered to be a hollow shaft, and the piston is considered to be a solid shaft. So you are seeing the cylinder that have a outside diameter and it have some thickness. That's what you will have inside diameter, both outside diameter and inside diameter. And inside the cylinder only piston is reciprocating. Due to the combustion, it is going to get on a gas pressure. That's what you will be having a pressure, maximum pressure inside the engine cylinder. That we will assign as a small p. And the thickness, that's what you are going to make a design calculation first. It's a thickness T. Okay, that thickness T is for thickness of a cylinder wall. Because as you have outside diameter and inside diameter, that means what you are having a cylinder thickness. And the Poisson ratio is 1 by m, and it is usually taken as 0.25 because we are considering cast iron. For the cast iron, we are having a usual Poisson ratio of 0.2. So now, while considering, as you have seen already, there is a longitudinal stress and the circumferential stress. If you are seeing the longitudinal stress is going to act on the longitudinal direction. So because of the gas pressure, it is going to act towards top dead center, from top dead center to bottom dead center, it is going to make a pressure, acting of pressure because of the combustion of a fuel. So that is what usually stress we will be knowing. Stress will be what? Force divided by area. And while you are considering about in this case of a cylinder, inside the cylinder, the force will be depending upon the inside diameter of the cylinder. So inside diameter of the cylinder, the cross section area is being what? Pi by 4 d square. That is the force acting area. It is inside the cylinder on the piston entire surface it is going to act. That is what the inside diameter of the cylinder is what equal to that of a piston diameter, piston outside diameter. That's what you are considering the capital D, inside diameter of the cylinder. On that area, the entire force is going to act. That's what pi by 4 d square d. And the area is, it is pi by 4 du square minus d square, because you are getting it as a hollow shaft area. So under the circumferential area, if you are seeing, it is going to act that hollow shaft cross section. So that you are subtracting do minus d square. So pi by 4 du square minus d square. So by that way, you will be getting what is the longitudinal stress. And as we had already seen, one is longitudinal stress, another is a circumferential stress. Now about a circumferential stress, in case of a circumferential stress, the stress is going to act for that entire length. So that is what you are considering the length of the piston and multiplied by pressure. Okay, so the diameter into length, that's what inside diameter. Okay, and into length, you will be going to get d into L into P, and area will be 2 times of the thickness, because cylinder liner left side one thickness will be there, right side one thickness will be there. So multiplying with 2 times of the thickness and for the length. That's what the cross section, longitudinal cross section you are considering, okay, for the circumferential stress. So that you are going to get this L and L can cancel, so that you are getting d into P divided by 2t. And this what L is being the length of the cylinder, and area, projected area is what you are calculating as 2t into L. Then net longitudinal stress, the formula will be, that is longitudinal stress, if you are seeing linear stress minus the lateral stress by into 1 by m. That is what Poisson ratio will be getting multiplied, so that you are getting sigma L minus sigma C by m. Similarly, for a circumferential stress, there is a sigma C minus sigma L by m. Okay, so that you will be calculating what is the net longitudinal stress and net circumferential stress. So once you are calculating it, then you will be having a thickness of cylinder wall that can be calculated using the thin cylindrical formula. That is what in the strength of material you have the formula for that. So T equal to D into P divided by 2 sigma C plus C. So here the P is what it is being the maximum pressure inside the cylinder, and the capital D is what, as we had already seen, that is being the inside diameter of the cylinder, or it is said to be a cylinder bore, that is in mm. And the sigma C is what? It is a permissible circumferential or tube stress for the cylinder material, that is expressed in megapascal, otherwise it can be said Newton per mm square. So usually its value is 35 megapascal to 100 megapascal depending upon the size and material of the cylinder. And this capital C is what allowance for reboring. So once the allowance for reboring, if you are choosing, that will be what it is depending upon the cylinder bore for IC engine, that will be chosen depending upon this table. The allowance for the case of a reboring will be chosen according to the diameter. So the diameter is 75 or 100, 150, 200, 250, 300, 350, 400, 450, 500. Then there will be a reboring clearance for that. That's what you will be having the values for depending upon the cylinder bore. So depending upon the cylinder bore, you are having the allowance for reboring. And the thickness of cylinder wall, that will be what it is usually varying from 4.5 mm to 25 mm or more than that, depending upon what is the size of the cylinder. Depending upon the size of cylinder, you will be having the variation of thickness of cylinder wall. So the thickness of cylinder wall may also be obtained by means of an empirical relation. That empirical relation is what? It is 0.045 into T. The T is being what? It is being the diameter of cylinder bore, and plus 1.6 mm is what empirical relation to identify the thickness of cylindrical wall. The other empirical relation is what it is follows as, it is being for a case of dry liner 0.03 D to 0.035 D. And thickness of water jet ball, that it is 0.03 D plus 1.6 mm. So otherwise it can be considered 1/3 of thickness of a wall. for a bigger cylinder, or 3/4 of the thickness of the wall for the case of a smaller cylinder. So water phase between the outer cylinder wall and the inner jacket wall will be equal to 10 mm for the case of 75 mm cylinder, and it varies to 75 mm for the case of a 750 mm cylinder. So otherwise, you have an empirical relation 0.08D plus 6.5 mm. That empirical relation also you can use for identification of what will be the thickness for the case of a different sizes of a cylinder. So next, the specification is what you will be having a bore length of the cylinder. So the bore is what inner diameter. Bore is said to be an inner diameter, capital D. We had first specification what we have seen is small t, that is the thickness of the cylinder wall. Now we are going to consider about the bore, capital D, and also the length of the cylinder that can be determined using this procedure. So now you are again considering these notations. P suffix m means what? It is indicated mean effective pressure in Newton by mm square, and capital D is what cylinder bore in mm, and capital A is cross sectional area of cylinder in mm square. Usually it's a circular cross section only. Cylinders and pistons, that assembly is being a circular one only, so that circular cross section area is being what? Pi d square by 4. Otherwise it can be written as pi r square if you are calculating it as a radius. And length will be what? It's a length of stroke in meters, small n, and capital N it indicates for speed of engine in RPM, and small n is the number of working strokes per minute. This small n, number of working strokes, can be considered as capital N equal to the speed of engine RPM in case of two-stroke engines. But if it is mentioned as two-stroke engine, then it will be considered half of the value of speed of the engine. And if you know that power produced inside the engine cylinder, that is indicated power, that indicated power relation with the mean effective pressure is indicated power equal to the mean effective pressure P suffix m into LAN by 60. So everything is mentioned. What is L is what it is being what already we have mentioned, it is being length of stroke, and A is being what area of cross section, and N we have seen a number of stroke. Already in the previous slide we have seen that. Okay. That is why we will be having a indicated power correlation with the mean effective pressure. And from this expression, we can able to identify what is the diameter or length of a stroke. Okay, length of a stroke L, as well as bore diameter of a cylinder, capital T. We can able to determine from this expression. So the length of stroke is what it is generally taken as 1.25 times of the D to 2D. Either it will be within this range 1.25 to 2D. Otherwise, we can take it as an average of this 1.25D to 2D. And since there is a clearance on both sides of a cylinder, therefore the length of the cylinder is taken as 15% greater than that of the length of the stroke. So other words, we can say that the length of cylinder L equal to 1.15 times into length of stroke. As we are getting adding of this 15%, so we are multiplying it with 1.15 into length of stroke, so that we are making a relation that the length of cylinder will be equal to 1.15 times of the length of stroke. So here, if the power developed at the crankshaft, that is the brake power, is in watts, and the mechanical efficiency of the engine is known, then we can consider that the indicated power that will be equal to brake power divided by mechanical efficiency, so that the maximum gas pressure may be taken 9 to 10 times the mean effective pressure. About cylinder flange and stress, that is the third specification, cylinder flange and stress. So cylinders are cast integral with the upper half of the crankcase, or they will be attached to the crankcase by means of a flange with stress or bolts and nuts. And the cylinder flange is integral with the cylinder and should be made thicker than the cylinder wall. You see the flange thickness that should be taken 1.2 times T to 1.4 times the T, where the T value is what? Thickness of cylinder wall. That's what we have seen in the design procedure first. And the diameter of the studs or bolts may be obtained by equating the gas load due to the maximum pressure in the cylinder to the resisting force offered by all the studs or bolts. And now, as we had seen, what is that gas pressure we had seen, so that we are going to make a equation. So the diameter of stud bolts may be obtained by equating the gas load due to the maximum pressure in the cylinder to the resisting force. So now mathematically we are seeing what is the maximum pressure due to the gas load. Due to the gas load, you will be getting area upon a piston pi by 4 d square multiplied by the gas pressure small p. That will be equated with the upon a resisting force. This is the resisting force. So in the case of an cylinder flange state, you will be considering Ns into pi by 4 dc square sigma t. You will be going to experiencing tensile stress. The bolts and studs is going to experience a tensile stress. So you are making the area on the cylinder flange and stud multiplied by the tensile stress into number of studs. How many studs you will be going to use. So that's what you will be seeing. Capital D is being a cylinder bore in mm and P is being a maximum pressure and Ns being how many number of studs you will be making use. That is what Ns. So that it can be taken, this value can be taken that 0.01 times of D plus 4. From that to the range is 0.02 D2 plus 4. So the DC is being what? This DC is being what? That is a core or a minor diameter. That is the diameter at the root of the thread. And also the sigma T is what allowable tensile stress for the material of the studs or spool. So this value is, if it is not mentioned in the problem, it can be taken 35 to 70 megapascal. And the nominal or major diameter of the stud or bolt that is usually lies between 0.75 times of the thickness of the flange to thickness of flange, where TF is what the thickness of flange. And if in case of no case, yes, if it is not specified clearly, then a stud or bolt less than 60 mm diameter should be used. And the distance of the flange from the center of the pole for the stud or bolt should not be less than the D plus 60 mm, and it should not be more than that of 1.5 times of the D, where the small d is what the nominal diameter of the stud or bolt. So in order to make a leaf-proof joint, the pitch of the studs or bolt should lie between 19 square root of D to 28.5 square root of D, where the small d is in mm. And finally, the cylinder head. In case of cylinder head, usually here above the cylinder there will be a cylinder head. A separate cylinder head or cover is provided with most of the engine. It is usually made of a box-type section of considerable depth to accommodate ports for air and gas passages, inlet valve, exhaust valve, and spark plug. In case of a petrol engine, you will be having a spark plug or atomizer at the center of the cover. That is in case of a diesel engine. So the cylinder head may be approximately taken as a flat circular plate whose thickness may be determined from the following relation. So the thickness of cylinder head that will be calculated using capital D into square root of C into small d by sigma c, where the capital D is being what cylinder bore in mm and small b is maximum pressure inside the cylinder in Newton per mm square, and sigma c is allowable circumferential stress in megapascal or Newton per mm square. And this is approximately taken the value 30 to 50 megapascal, and C is the constant whose value is taken as 0.1. So the studs or bolts are screwed up tightly along with the metal gasket or asbestos backing to provide a leak-proof joint between the cylinder and cylinder head. The tightness of the joint also depends upon the pitch of the bolts or studs. That should lie between 19 square root of D to 28.5 square root of D. The pitch circle diameter is usually taken as D plus 3D. The studs or bolts are designed in the same way as discussed above. Now we will see a problem using this design procedure. A 4-stroke diesel engine, as I already mentioned, that small n value will be taken equal to the speed of engine, capital N, if it is being a 2-stroke engine. And if it is a 4-stroke engine, that will be considered half of that. That's what here you will be seeing that notation, 4-stroke diesel engine. Okay, a 4-stroke diesel engine, brake power is given and the speed n value is given. Indicator mean effective pressure is given, mechanical efficiency given. It is required to determine what is the bore and length of the cylinder, what is the thickness of cylinder head, and what is the size of the studs for the cylinder head. So first step, you are writing this given data. So brake power, mentioned brake power is 5 kilowatts, so you are converting into 1 watts, and the speed is given 1200 rpm. So you are making it, it's being half of the speed, small n value. So small n value is n by 2, so that is what you have a 600 rpm for the case of number of two, and the PM value, that is what mean effective pressure is given 0.35 Newton per mm square, and mechanical efficiency is given 80%, 0.8. And we are also indicated power. We have a formula connecting with this mechanical this mean effective pressure, and also mechanical efficiency and brake power having correlation with that of indicated power. So that formula we are going to combine, and we are going to identify the unknown specifications. Okay. So now first thing is what a calculation of bore and length of cylinder. So let T equal to bore of a cylinder in mm, and capital A is being what cross-sectional area of the cylinder, so that is being pi by 4 d square in mm square, and L being what length of stroke in meter. So now, so that will be equal to 1.5 times of the d in mm, because we had already seen what will be the length of stroke. That will be taken in between 1.25 to 1.5 d. Already we have seen in the design procedure. So that relations only we will be making use. That is given in mm, and for converting into meter, we have to divide it bit by 1000. Then it will be converted into a meter. Then we know the indicated power. For indicated power, we have a formula. So the indicated power will be what? It is equal to brake power by efficiency mechanical. And also it have PM into that lag by 60 is there. Okay, that we will correlate at later stage. Okay. So now indicated power, brake power is here, efficiency mechanical is here. From that we can able to directly identify what will be the indicated power. So the brake power given is what 5000 watts. So 5000 watt, and the efficiency mechanical is 0.8. So by making it calculation 5000 by 0.8, you are getting an indicated power 6250 watts. Now we are going to make a calculation of indicated power using that formula PM into LAM by 60. So we calculated indicated power as 6250 watts. So now we are making utilization of this formula PM into L into A into N divided by 16. So on that we know about a PM, that is 0.35. This PM value is given in the question itself, that is being 0.35 Newton per mm square. And L we had considered 1.5 times that of D, and A is what pi d square by 4. Okay, 4 is coming this side. Okay, and also this 1.5 times of the D for conversion into the case of an mm, you are dividing by 1000. That's how this 1000 is coming here. And this N value is what 1200 RPM is capital N, but small n is capital N by 2, so that we have got it as 600. So that's what you have substituted here. So that by simplifying this calculation, you will be getting, so d is here and d square is here, you are going to get d cube. By making these calculations, you are going to get 4.12 into 10 power minus 3. This is for the 4-stroke engine. For 4-stroke engine, we consider N is equal to capital N by 2. So small n equal to capital N by 2. That's what the calculation you have made. So now here the D value can be identified from this, because you have already calculated value is here, and only unknown is what capital D. So now we can able to calculate what is capital D. So the DQ value is, for keeping this 6250, and this thing is simplified one taken to the left side means divided by 4.12 to 10 power minus 3. By calculation you are getting the value as D value as 115 mm. And from this, you had a correlation. L, length of the cylinder is being 1.5 times of D. So by substitution, you will be getting the length of the cylinder as being 172.5 mm. And also, you are taking a clearance, 15% of the stroke as on a clearance. By that, you are going to get what 1.15 times of the L will be what you are going to get the length of the cylinder. So you are going to get 1.15 times of the L. So you will be getting the length of the cylinder as 198 mm. That's you are saying approximately it is equal to 200 mm. And now coming to the second specification, the thickness of cylinder head. For a thickness of cylinder head, it is mentioned in the problem, and also in the design procedure we have seen. The maximum pressure in the cylinder can be taken 9 to 10 times the mean effective pressure. So therefore we can take, so the P value, the maximum pressure value will be 9 times of the mean effective pressure. So by that we are calculating the maximum pressure is being 3.15 Newton per mm square. And we know what is the thickness of cylinder head. We had a formula TH, it is equal to capital D square root of C into P by sigma C. So now we are substituting. Already we had calculated this D value as 115 mm. In the first step itself we had identified. So that value we are taking here 115 mm. On the C value we are going to take from the table. Already we had said it in the design procedure. Now we calculated P value 3.15, and this is being sigma C is being taken as 42 megapascal. So taking C value as 0.1 and sigma T as 42 megapascal. By calculating, you are getting the answer as 9.96, and you are saying rounding it to 10 mm. So 10 mm is what the answer for the thickness of cylinder head. And the next thing, size of studs for the cylinder head. So small d is the nominal diameter of the stud, and the d suffix c is for the core diameter of the studs in mm. It is usually taken as 0.84 d. That's what we have discussed in design procedure. And the sigma t is for the tensile stress for the material of the stud, which is usually a nickel steel. And ns is number of studs. So we know the force acting on the cylinder head. That will be what the force acting on the cylinder head is pi by 4 into d square. That is what area of a piston also. That is what inside the diameter of the cylinder. That is pressure is acting. Okay. So the gas pressure is acting pi by 4 d square into t. So d value we had calculated as 115 square, and p value maximum pressure we calculated as 3.15. So from there you are calculating the force value as 32.702. So this you are keeping as equation 1. Then number of steps are usually taken between 0.01d plus 4 and 0.02d plus 4. This we have discussed already in the design procedure. So now you are taking ns value. You are assuming it's for a better design. Usually the 6 studs will be used. So that's what for the cylinders. It is a standard one. So we are taking the standard values of 6. Number of studs we had assuming as 6. Then we had calculated already the cylinder head force is being what 32.702, and now we are taking the number of steps is being C. Now we are going to make equating this pressure to resisting force offered by all studs. This pressure force acting on the cylinder head that will be withstood by the all the studs. So it should have the resisting force. What is the gas pressure acting? That should be resisted by all the studs. So that is what now you are making equation. So ns into pi by 4 dc square into sigma t. This is also we got seen in the design procedure. Okay. So now ns value is 6 and the dc value we had taken 0.84 times of d, and the sigma t value we are taking it as 65 megapascal. So that is what 65 Newton per mm square. So you are making it 216 d square. By calculation you are getting 216 d square. So this will be equated to 32.702. So that you can identify what will be the diameter of studs. Small d can be identified from this. So you are equating, so 32.702 divided by 216, so that you are calculating the d value. D value is getting 12.3. So you are rounding it, and you are saying the diameter of the cylinder head is being 14 mm. So the diameter of stud you have identified as 14 mm. So now with the help of that you are identifying what is the pitch circle diameter of the studs. That will be taken as d plus 3d. So you are substituting the diameter of studs, so that you are identifying what is the pitch circle diameter of the studs. And we know the pitch of the studs. Pitch of the studs is pi into d suffix p by ns. By substituting this calculated value of pitch circle diameter, you can identify what will be the pitch of the studs. And also finally, you can see this correlation. So for the leak-proof joint, the pitch of the stud should be between 19 square root of d to 28.5 square root of d, where d is for the nominal diameter of stud. So by substituting the nominal diameter calculated 14 mm, you can identify what is the minimum pitch of the stud and what is the maximum pitch of the stud. By calculation, you are getting minimum pitch of the stud is being 71.1 mm and the maximum pitch of the stud as 106.6 mm. So since the pitch of the studs obtained is what it is 82.2 mm, that is lies within the 71.1 mm and 106.6 mm. We had a minimum pitch and maximum pitch, which in that only the pitch of the stud is lying. So as it is lying within the minimum pitch and the maximum pitch, the design is said to be satisfactory. Suppose if it is not lying within this one, then you have to make changing of a diameter. That is what the design concept. If it is coming within the limit means design is satisfactory. Otherwise, you need to have a variation of dimensions. That is what the design procedure is. Okay. So thank you very much. And the next video class you will see about the next module. So this one is cylinder. Next module we will concentrate with connecting rod.